All right, so looking at 3.9, the last section of chapter 3, dealing with rules for derivatives, we're looking at the derivatives of exponential and logarithmic functions. All right, first thing, let's look at the graph of y equals e to the x. Now, the slope at x equals 0 appears to be 1. We go up 1 and over 1 to here, and we go down 1 and over 1 to here. So it looks like that slope looks to be 1 right there at x equals 0. Well, if that's true, then we know this is the case. The limit as h approaches 0 of e to the 0 plus h minus e to the 0 over h equals 1. Now where that comes from, if you remember the definition of the derivative, was the limit as h approaches 0 of f of x plus h minus f of x all over h. So what we're saying here, our function is e to the x, and we're evaluating it at 0. So we're putting a 0 in everywhere we got an x, and our function is e. So e to the x plus h minus e to the 0 all over h. Now remember, e to the 0 here is 1. That's going to come into play here in just a second. But right now, let's just assume that part right there, and we're going to assume it to be true. Now, if we attempt to find a general formula for the derivative of y equals e to the x, using the definition, we have d dx of e to the x is equal to the limit as h approaches 0 of e to the x plus h minus e to the x all over h. So we're finding a general solution or a general equation for it this time. So we can think of this right here much like we did with much like we did before. What we're doing right here, let me go ahead and show. If we have x to the third power times x to the fourth power, we know that's x to the seventh. But how did we get there? Well, we added our powers. So what we have here is x to the 3 plus 4. So we're actually doing this backwards. So where we have e to the x plus h, we now have e to the x times e to the h. So that's what we're doing, and we split that thing up. Now we have a situation where we have an e to the x that's common with both of our terms here. So what we can do, and it's not affected by this limit. Remember, the limit is doing what? It's letting h go to 0. It's not affecting x at all. So we can actually take this e to the x that's common to both terms on top and pull it all the way out front. So we have e to the x times the limit as h approaches 0 of e to the h minus 1 all over h. Now, think back to what we just dealt with. Well, remember, we said that the limit on the previous page, the limit as h approaches 0 of e to the 0 plus h minus e to the 0 over h was equal to 1. All right, so do you see where I'm going now? Well, what is 0 plus h? That's just e to the h, right? And what is e to the 0? Well, that's just 1. So we're saying, or we did say, that the limit as h approaches 0 of e to the h minus 1 over h was equal to 1. So that means that this value right here is 1. So we have e to the x times 1, which equals e to the x. So we're saying that the derivative with respect to x of e to the x is itself. And that's exactly true. So the derivative with respect to x of e to the x is e to the x. As long as you continue to derive it, you're going to get the exact same thing back over and over and over again until You do the power, the chain rule, and this up here becomes something that whose derivative is not 1. So e to the x is its own derivative. That leads us to the chain rule definition of the derivative with respect to x of e to the u is equal to e to the u times the derivative of u with respect to x. So, for instance, if we have, let's say, e to the x squared that we're taking the derivative of, it's going to start off with e to the x squared, e to the u, and then we have to multiply by the derivative of whatever the power is. So it's going to be 2x. So we end up with 2x e to the x squared. That would be your derivative. Now we can use this formula to also find the derivative of a to the x. Now a to the x is anything other than e. So 2 to the x, 3 to the x, 7 to the x, all those things. You can't use this rule right here for those. You can only use this for e. Remember, e is a constant value of 2.71828 that continues on forever and ever. This is specific only to e. So if we do a little bit of playing around here with our inverse functions, e times e to the natural log of a to the x is the same thing as a to the x, because we're actually introducing this so that we can deal with it. But those would cancel out and leave us with a to the x. We're just going backwards. All right, and then we can use the power rule to move that x out here. And then we have e to the x natural log of a, that's the derivative of that, times the derivative of x times the natural log of a. And that right there is a constant. The natural log of a is a constant, so it's essentially like saying, what's the derivative of 2x? It would be 2, except the derivative here is going to be the natural log of a. Now, once again, remember that e to the natural log of a to the x is just a to the x, so we can rewrite that as a to the x times the natural log of a. So that's the only thing that changes when we're dealing with something that is an exponential that's base is not e. We have to tag on the natural log of whatever the base is. Now, guys, I'll be honest with you, this is the better rule to remember, because if a happens to be e, what happens? You get e to the x natural log of e. And what's the natural log of e? Well, that's just 1. So it's not going to change it. This is the catch-all for exponentials. That rule right there will help you, will let you do every exponential derivative that you'll ever have to do. If you only remember the one for e, that one only applies when the base is e. Anything else, you get a 2 to the x and you don't know how to do it if this is all that you've remembered. So this is the one that you want to remember. You want to use that as the catch-all, and just remember that the natural log of e is 1. So if you incorporate the chain rule, you have d dx of a to the u equals a to the u times the natural log of a times du dx. Guys, this is not on your equation sheet, your derivative sheet. You want to write that down on there. The derivative sheet that I gave you, you're going to want to write that down on there somewhere. All right, so far we have the derivative of e to the u and the derivative of a to the u, with a being any exponential with a base other than e. Now remember, exponentials cannot have bases that are negative or 0 or 1. That's the rules for having for what an exponential expression actually is. So be careful. Don't think that is going to apply if this is a negative or if it's 0 or 1. It doesn't work that way. All right, so now it's relatively easy to find the derivative of the natural log of x. All right, so we start off with y equaling the natural log of x. And we're going to do something very similar to what we did in the last section with finding the derivative of the inverse trig function. We're going to implicitly differentiate this with things we already know to do. So if y equals the natural log of x, we can exponentiate both sides, and we get e to the y is equal to x. So if we take the derivative of both sides, we're going to end up with e to the y dy dx equals 1. Well, we can solve for dy dx to find out what the derivative of natural log is, and we find out that it's 1 over e to the y. Well, the thing is, we also know that e to the y equals x because we found it in the very second step here. So we can interchange e to the y with x, and we end up with, since y is natural log of x, the derivative of natural log of x with respect to x is 1 over x. Now that gives us our rule, including the chain rule, that says derivative with respect to x of natural log of u is 1 over u du dx. Now you also will sometimes see this as u prime over u. Guys, one of the things that you're going to find, especially when we get into the integration part or the anti-differentiation where you're doing these backwards, you're going to think 1 over anything is a natural log. Well, it's not. It has to be the derivative of whatever's on the bottom on top, or it's not a natural log. So you've got to have the derivative of the bottom on the top, or this thing's not a natural log. So a lot of people will think later on that 1 over x squared, if we're integrating this with respect to x, is the natural log of x squared. Well, there's only one problem. That's not true. So be careful. Make sure you understand that it's u prime over u, or 1 over u times du dx. That's where the u prime is. U prime is nothing more than du dx. Just another way of writing it. Now, to find the derivative of a common log function, you could just change the base of formula. You could use the change of base rule for logs. So if we had a common log of x, we can change that by using the change of base rule. It's the natural log of x over the natural log of 10. And when you take the derivative, the 1 over the natural log of 10 is a constant, so it can move all the way out to the front. And what do we know the derivative of natural log of x is? Well, it's 1 over x. So we end up with 1 over the natural log of 10 times 1 over x. So this is very similar to what we dealt with when we used an exponential expression with a base that was not e. We had to multiply that. In that case, we had to multiply by the natural log of whatever the base was. In this case, we're going to have to divide by it. But you can always use the change of base formula as an easy way to remember that the natural log of the base should be on bottom. So if we were to take the, not natural log, let's say the log base 2 of x squared. Well, all we're going to do is take the log of x squared. We take its derivative. We're going to end up with 1 over 2, natural log of 2 that is, and then multiply by the derivative of the natural log of x squared. And that's going to be 2x over x squared. Now notice what happens here. This will actually simplify down. This x will cancel out with one of those, and you end up with 2 over the natural log of 2 times x. And that's just putting everything together. And you could move, I would actually rather move that x out in front there. So 2 over x natural log of 2. That way you don't mistake the fact that it's the natural log of 2x. It's actually not. It's the natural log of 2 times x. All right, so the formula for the derivative of the log of any base other than e, in other words, any log that's not a natural log, is this thing right here. Derivative with respect to x of log base a of u is 1 over u times the natural log of a, the base, times du dx. And you could also put u prime up here and knock off the du dx. All right, and guys, this one is another one of those equations that is not on your derivative sheet, so you want to copy that on there. Once again, this is the catch-all. Remember, if this is a log base e, well, natural log of e would be 1, so you'd end up with 1 over u times du dx. This is the catch-all. If you remember this one, you remember all of them. If you remember just the natural log one and you get a log base something other than e, well, you're stuck unless you remember both of them. All right, so here are all of our new rules. These two are on your sheet. These two are not. Make sure they get on there. So those are the new rules that we've learned for today, the last set of rules for Chapter 3. And we've got one more thing to look into, and it's logarithmic differentiation. So we're going to find dy dx of y equals x to the x power. Now you're going to notice here, this is a little different than anything we've dealt with so far. Y equals x to the x. Now the question is, how do we qualify this? What does this thing classify as? Is this a power rule problem? Well, no, because if you remember, a power rule problem has an x, the base, that is a variable, but the power is a constant. So we would use the power rule on something like x to the third. So that's not the case we're looking at. Well, would it be an exponential function? Well, no, because an exponential function has a base that's a constant and a power that's a variable. So that's not going to apply here either. So what we end up having to do is a special kind of integration or differentiation called logarithmic differentiation. And the way we're going to do this is we're actually going to take the natural log of both sides. Natural log of y equals the natural log of x to the x power. Now, for those of you that are quick and know your log rules, you hopefully spot the first thing that you're going to do here now, and that is use the power rule for logs to move this out front. So the natural log of y ends up being x times the natural log of x. Now, once you do that, you need to differentiate it. When you're going to differentiate both sides, you're going to have over here 1 over y dy dx, because we are doing implicit differentiation here. So we took the derivative of natural log of y, and we get 1 over y times dy dx. That's what we're going to end up solving for, by the way. And over here, lucky us, we have a product. So we're going to have to use a product rule. We have x times the natural log of x. So first, times the derivative of the second, derivative of natural log of x is 1 over x, plus second, natural log of x, times the derivative of the first, which is 1. All right, so we end up with 1 over y dy dx, and when we simplify this other side over here, x times 1 over x is 1. Natural log of x times 1 is natural log of x. And we're almost done. There's only one problem. We've got 1 over y over here. We need to solve for dy dx. So we're going to move the 1 over y to the other side by multiplying both sides by y. So we move up here, and we're going to end up with dy dx is equal to y times 1 plus the natural log of x. Now, we don't want to leave it like this because we want to express our derivative, if at all possible, in terms of y of x only. Well, is there a way that we can get rid of this y and put it in a term of x? Well, we've seen this a couple of times in the last two sections. There's algebra, so if two things are equal, they are interchangeable. So that means that since y started out as x to the x, we can put x to the x right here. So my dy dx actually ends up being x to the x times 1 minus the natural log of x. Sorry, that's 1 plus. So that is our solution. Now you're going to need to use logarithmic differentiation anytime you have a situation where both the base and the power are variables, even if they're not the same variable. Now you're probably not going to see one of those, but you may see x to the 3x or something like that, or x to the x squared. Those are all going to be situations that you would use logarithmic differentiation for. So if you have a degree and the base that are both variables, that's where you use logarithmic differentiation, simply because you can use this rule right here to move that power out in front and then use the product rule. That's where you use logarithmic differentiation. All right, that is all of section 9 and all of chapter 3. So that is the last of the derivative rules.